So hello and welcome to the video. I am Vishnu Das and today I am going to talk about the Turing machine in detail. So this is a pic of the Turing machine. So a Turing machine. A Turing machine is an accepting device which accepts the language's recursively enumerable set generated by type 0 grammars. It was invented in 1936 by Alan Turing. Definition: a Turing machine is a mathematical model which consists of an infinite length tape divided into cells on which the input is given. It consists of a head which reads the input tape. A state register stores the state of the Turing machine. After reading an input symbol, it is replaced with another symbol, its internal state is changed, and it moves from one cell to the right or left. If the Turing machine reaches the final state, the input string is accepted, otherwise rejected. A Turing machine can be formally described as 7 tuple, where Q represents the finite set of states, X represents the tape alphabet, sigma represents the input alphabet, del represents the transition function, Q0 is the initial state, B is the blank symbol, and F is the final set of states. So the comparison with the previous automaton. The following table shows a comparison of how Turing machine differs from finite automaton and push-down automaton. A finite automaton, the stack data structure is not available and it is deterministic. Push-down automaton, it is last in first out, whereas it is non-deterministic. Turing machine is an infinite tape and it is deterministic. So the example of Turing machine, the Turing machine M is equal to Q, X, sigma, del, Q0, B and F, with Q representing Q0, Q1, Q2 and Qf, X representing A and B, sigma representing 1, Q0 representing Q0, B is the blank symbol and the F representing Qf, and del is given by tape alphabet symbol A. Present state Q0 is 1R Q1, present state Q1 is 1L Q0, present state Q2 is 1L Qf. For the tape alphabet symbol B, present state Q0 is 1L Q2, present state Q1 is 1R Q1 and the present state Q2 is 1R Qf. Here the transition 1R Q1 implies that the right symbol is 1, the tape moves right and the next state is Q1. Similarly, the transition 1L Q2 implies that the right symbol is 1, the tape moves left and the next state is Q2. So the time and space complexity of a Turing machine. For a Turing machine, the time complexity refers to the measure of the number of times the tape moves when the machine is initialized for some input symbols, and the space complexity is the number of cells of the tape written. The time complexity of all reasonable functions Tn is equal to O n log n. Turing machine space complexity is O n. So the accepted language and the decided language. A Turing machine accepts a language if it enters into a final state for any input string W. A language is recursively enumerable generated by type 0 grammar if it is accepted by a Turing machine. A Turing machine decides a language if it accepts it and enters into a rejecting state for any input not in the language. A language is recursive if it is decided by a Turing machine. There may be some cases where a Turing machine does not stop. Such Turing machine accepts the language but does not decide it. So, designing a Turing machine. The basic guidelines of designing a Turing machine have been explained below with the help of a couple of examples. Example 1. Design a Turing machine to recognize all strings consisting of an odd number of alphas. Solution. The Turing machine M can be constructed by the following moves. Let Q1 be the initial state. If M is in Q1 on scanning alpha, it enters Q2 and writes B blank. If M is in Q2 on scanning alpha, it enters the state Q1 and writes B blank. From the above moves, we can see that M enters the state Q1 if it scans an even number of alphas, and it enters the state Q2 if it scans an odd number of alphas. Hence Q2 is the only accepting state. Hence M is equal to Q1, Q2, 1, B, del, Q1, B, Q2. Where del is given by tape alphabet symbol alpha. Present state Q1 is BRQ2 and the present state Q2 is BRQ1. Now example 2. Design a Turing machine that reads a string representing a binary number and erases all leading zeros in the string. However, the string comprises of only zeros, it keeps 1 0. Solution. Let us assume that the input string is terminated by a blank symbol b at each end of the string. The Turing machine M can be constructed by the following moves. Let Q0 be the initial state. If M is in Q0, on reading 0 it moves right, enters the state Q1 and erases 0. On reading 1 it enters Q2 and moves right. If M is in Q1, on reading 0 it moves right and erases 0. That is, it replaces zeros by b's. On reaching the leftmost one it enters Q2 and moves right. If it reaches b, that is, the string comprises of only zeros, it moves left and enters the state Q3. If M is in Q2, on reading 0 or 1 it moves right. On reaching b, it moves left and enters the state Q4. This validates that the string comprises only of zeros and ones. If M is in Q3, it replaces b by 0, moves left and reaches the final state Qf. If M is in Q4, on reading either 0 or 1, it moves left. On reaching the beginning of the string, that is, when it reads b, it reaches the final state Qf. Hence, M is equal to Q0, Q1, Q2, Q3, Q4, Qf, comma 0, comma 1, comma b, comma 1, comma b, comma del, comma Q0, comma b, comma Qf, where del is given by the tape alphabet symbol 0, the present state Q0 is BRQ1. For the present state Q1, it is the same BRQ1. For the present state Q0 is ORQ2. For the present state Q3, it is not given. For the present state Q4, it is OLQ4. For the tape alphabet symbol 1, the present state Q0 is 1RQ2. The present state Q1 is 1RQ2. For the present state Q2, it is 1RQ2. For the present state Q3, it is not given, and the present state Q4 is 1LQ4. For the tape alphabet symbol B, the present state Q0 is BRQ1. The present state Q1 is BLQ3. The present state Q2 is BLQ4. Present state Q3 is OLQF, and the present state Q4 is BRQF. Multi-tape Turing machine. So a multi-tape Turing machine have multiple tapes where each tape is accessed with a separate head. Each head can move independently of the other heads. Initially the input is on tape 1 and the others are kept blank. At first the first tape is occupied by the input and the other tapes are kept blank. Next the machine reads the consecutive symbols under its heads and the Turing machine prints a symbol on each tape and moves its heads. A multi-tape Turing machine can be formally described as a 6-tuple, where Q is a finite set of states, X is the tape alphabet, B is the blank symbol, del is a relation on states and symbols where del is Q into X to the power K, which is equivalent to Q into X into left shift, comma right shift, comma number of shift to the power K, where there is K number of tapes. Q0 is the initial state and F is the set of final states. Note, every multi-tape Turing machine has an equivalent single-tape Turing machine. Now we have the multi-track Turing machine. So the multi-track Turing machines are a specific type of multi-tape Turing machines containing multiple tracks but just one tape head reads and writes on all the tracks. Here a single tape head reads n symbols from n tracks at one step. It accepts recursively enumerable languages like a normal single-track, single-tape Turing machine accepts. A multi-track Turing machine can be formally described as a 6-tuple, where Q represents the finite set of states, X is the tape alphabet, sigma is the input alphabet, del is the relation on states and symbols where del Qi, comma, A1, A2, A3 up to infinite, which is equal to Qi, comma, B1, B2, B3 up to an infinite, comma left shift or right shift. Q0 is the initial state and F represents the final set of states. For every single track Turing machine S, there is an equivalent multi-track Turing machine M such that LS is equal to LM. Now the non-deterministic Turing machine. In a non-deterministic Turing machine, for every state and symbol, there are a group of actions that a Turing machine can have. So here the transitions are not deterministic. The computation of a non-deterministic Turing machine is a tree of configurations that can be reached from the start configuration. An input is accepted if there is at least one node of the tree which is an accept configuration. Otherwise, it is not accepted. If all the branches on the computational tree halt on all the inputs, the non-deterministic Turing machine is called a decider, and if for some input all branches are rejected, the input is also rejected. A non-deterministic Turing machine can be formally described as 6-tuple, where Q is the finite set of states, X is the tape alphabet, sigma represents the input alphabet, del is the transition function where del is q into x, which is equal to p into q into x into left shift or right shift. Q naught is the initial state and V is the blank symbol and F is the set of final states. So a semi-infinite tape Turing machine. A Turing machine with a semi-infinite tape has a left end but no right end. The left end is limited with an end marker. It is a two-track tape. Upper track, it represents the cells to the right of the initial head position. Lower track, it represents the cells to the left of the initial head position in reverse order. The infinite length input string is initially written on the tape in contiguous tape cells. The machine starts from the initial state Q0 and the head scans from the left end marker end. In each step, it reads the symbol on the tape under its head. It writes a new symbol on that tape cell and then it moves the head either to the left or right one tape cell. A transition function determines the actions to be taken. It has two special states called accept state and reject state. If at any point of time it enters into the accepted state, the input is accepted, and if it enters into the reject state, the input is rejected by the Turing machine. In some cases, it continues to run infinitely without being accepted or rejected for some certain input symbols. Note: the Turing machine with semi-infinite tape are equivalent to standard Turing machines. So now we have the linear bounded automata. So a linear bounded automata is a multi-track non-deterministic Turing machine with a tape of some bounded finite length, where length is the function of length of the initial input string and constant c. Here memory information is less than or equal to c into input information. The computation is restricted to the constant bounded area. The input alphabet contains two special symbols which serve as the left end markers and the right end markers, which mean the transitions neither move to the left of the left end marker nor to the right of the right end marker of the tape. A linear bounded automaton can be defined as an 8-tuple where Q represents the finite set of states, X is the tape alphabet, sigma is the input alphabet, Q0 is the initial state, ML is the left end marker, MR is the right end marker where MR not equal to ML, del is the transition function which maps each pair, state and tape symbol to the state, tape symbol and constant C, where C can be 0 or +1 or -1, and F represents the set of final states. A deterministic linear bounded automaton is always context sensitive, and linear bounded automaton with empty language is undecidable. So this is all about the linear bounded automata. So now the language decidability. A language is called decidable or recursive if there is a Turing machine which accepts and halts on every input string W. Every decidable language is Turing acceptable. A decision problem P is decidable if the language L of all yes instances to P is decidable. For a decidable language, for each input string, the Turing machine halts either at the accept or the reject state as depicted in the following diagram. So now the example 1. Find out whether the following problem is decidable or not. Is a number m prime. Prime numbers are 2, 3, 5, 7, 11, 13, etc. Divide the number m by all the numbers between 2 and root m starting from 2. If any of these numbers produce a remainder 0, then it goes to the rejected state, otherwise it goes to the accepted state. So here the answer could be made by yes or no. Hence it is a decidable problem. So the example 2. Given a regular language L and string W, how can we check if W belongs to L? Solution. Take the deterministic finite automata that accepts the language L and check if W is accepted. So some more decidable problems are: does DFA accept the empty language? Is L1 intersection L2 is equal to 5 for regular sets? Note: if a language L is decidable, then its complement L' is also decidable. If a language is decidable, then there is an enumerator for it. So an undecidable language. An undecidable language, there is no Turing machine which accepts the language and makes a decision for every input string W. The Turing machine can make decision for some input string though. A decision problem P is called undecidable if the language L of all the yes instances to P is not decidable. Undecidable languages are not recursive languages, but sometimes they may be recursively enumerable languages. Example: the halting problem of Turing machine, the mortality problem, the mortal matrix problem, and the post correspondence problem, etc. The Turing machine halting problem. Input: a Turing machine and an input string W. Problem: does the Turing machine finish computing of the string W in a finite number of steps? The answer must be either yes or no. Proof: at first we will assume that such a Turing machine exists to solve this problem, and then we will show it is contradicting itself. We will call this Turing machine as a halting machine that produces yes or no in a finite amount of time. If the halting machine finishes in a finite amount of time, the output is yes, otherwise no. The following is the block diagram of a halting machine, where the input string is taken and the answer is either yes or no. Now there is the inverted halting machine. Now we'll design an inverted halting machine hm dash as: if h returns yes, then loop forever. If h returns no, then halt. The following is the block diagram of an inverted halting machine, where it takes an input string and produces either yes followed by an infinite loop or no. Further, a machine hm2 which input itself is constructed as follows: if hm2 halts on input, loop forever, else halt. Here we have a contradiction, hence the halting problem is undecidable. So the applications of a Turing machine. Check the decidability. If the Turing machine cannot solve a problem in a countable time, then there could not be any algorithm which could solve that problem. That is, the problem is undecidable. For a decidable problem, if its Turing machine halt in countable time for all finite length inputs, then we can say that the problem could be solved by an algorithm in countable time. Classify the problem. Turing machine helps to classify decidable problems into classes of polynomial hierarchy. Suppose we found that a problem is decidable, then out target become how efficiently we can solve it. The efficiency being calculated in the number of steps, extra space used, length of the code or size of the FSM. Design and implement algorithm for practical machines. Turing machine helps to propagate idea of algorithm in other practical machines. After the successful check of 1 and 2 criteria, we can use our practical devices or computers to design and implement the algorithm. So this was about the applications of a Turing machine. So this is all about the Turing machine, its logical and its practical applications. Hope you liked and enjoyed the video. Thank you.